Namaskar everyone. My dear students, I welcome you all to this next wonderful lecture of fluid mechanics. How are you all today? I hope all of you are fine, and early morning we are meeting, and let us work hard towards our goal. Okay, so I will discuss a few things, but the conformity about those things I will get after the break. After the break, the conformity about your next subject as well as the class, I will get after the break. Okay, so let us continue our journey in fluid mechanics, and let us learn turbulent flow and drag and lift. So today's lecture we are going to start with turbulent flow, and we are going to start with drag and lift. So these two topics we are going to cover now, so that our theory portion gets completely over. Ajay Raj, I have already discussed all the pressure gradient question. All the pressure gradient questions I have already discussed. Navier-Stokes equation, already I have discussed the pressure gradient question, Ajay Raj. Navier-Stokes, I have already discussed. In that I have beautifully told in your batch how to find the pressure gradient vector. Wonderful. I'm fine. Chaliye, let us start a mind-boggling lecture of fluid mechanics. My dear students, before starting anything, just tell me in the comment box, are you guys alive? Should we start today's lecture? Are you guys alive? Should we start today's lecture? Yes, wonderful. Chaliye, okay, yes, everything is fine and we should start. Chaliye beta, first of all, we will learn turbulent flow. First of all, we will learn turbulent flow. So come to page number 207 of your printout. Come to page number 207 of your printout. Come to page number 207 of your printout. Very good. Chaliye. Let us start with something which is known as turbulent flow. So the class is starting. Be highly attentive now. The class is starting. Be highly attentive now. Look here everyone. My dear students, this topic which is turbulent flow is actually highly research oriented topic. It is actually highly experiment based topic. It is there. So unfortunately I will have to say this, that almost in this last topic of fluid mechanics, as this topic is mainly experiments based, so all the results which are coming in this topic now are coming from experiments, and it is quite unfortunate that we will have to remember all the formulas. There is no choice in us in that. So in this particular chapter, my dear students, we will have to mug up a lot of formulas. Unfortunate, quite unfortunate to say this, because in complete fluid mechanics, beautifully I have given you the feel of a lot of stuff. But today, in this topic that is turbulent flow, I will have, you people have to mug up a lot of things, a lot of formulas. But this is the way it is. I can't help it. So this topic, as it is highly research oriented, highly experiment oriented, so turbulent flow, basically the major portion of turbulent flow is taught in master's level studies. But at BTech level, in UPSC and in GATE paper, it is clearly mentioned in your syllabus. They are saying in the syllabus, elementary turbulent flows. Elementary turbulent flows. Elementary turbulent flows. So he is clearly mentioning in the syllabus, elementary word is written in our syllabus, elementary turbulent flows. And already I told you this thing, that three topics, turbulent flow, vortex motion and dimensional analysis, not many questions have been asked in your examination. So if you will see the last 20-25 years previous year paper, not many questions, only might be 5 to 6 questions have been asked from turbulent flow in your examination. Okay, so this means this topic we are not going to go much into the details of a lot of things. I will only focus on this topic with respect to examination only, because yes, this topic is highly research oriented, so I will focus only from your GATE and UPSC perspective only. That's it. Now what is a turbulent flow? Please keep this thing in mind. Now what is a turbulent flow? Already we know the definition of turbulent flow. A turbulent flow is the one in which the fluid highly random motion is there. There is huge order intermixing of fluid particle is there, and the high order intermixing of fluid particles is there, and such a fluid flow is known as a turbulent flow. You know, a fluid flow is always an unsteady flow, because the properties of the fluid due to this huge order intermixing will keep on changing with space and time, will keep on continuously changing with space and time. Of course, due to intermixing there is a huge havoc and the problem is there. Apart from this, everybody should be knowing that whenever you know there are a lot of changes are there in the fluid properties. अगर fluid properties में बहुत सारे changes होने लगते हैं, if there are a hell lot of changes in the fluid properties are there, then scientists have devised a method to then how to study these variations which are happening so fast. So they have devised a method. Now what is that method we should know? See, any property, they have devised a method that any property in turbulent flow, can be written as a combination of. Any property in turbulent flow can be written as a combination of average component, and fluctuating component. Average component and fluctuating component. So it is written as a combination of average component and fluctuating component. See, it is not the first time that in science we are facing something whose variation is happening in milliseconds, microseconds or things like that. Because due to huge order intermixing, the properties are going to change so rapidly. But this is actually not the first time in science that we are facing this kind of a topic where the things are varying in a very fast manner with space and time. So scientists have devised a method to study the various properties in turbulent flow. They said that any property in turbulent flow can be written as a combination of average component and the fluctuating component. Average component and the fluctuating component. Average component and the fluctuating component. Now see, for example, what is the meaning of this? For example, let us say a fluid particle is there. And that fluid particle, let us say at this current moment of time, that fluid particle is having a velocity of 4.1. Then continuous intermixing is taking place. Then due to intermixing, let us say the velocity of the fluid particle has changed from 5.1 to let us say 5.5. It has changed from to 3.5. It has changed to 2.5. It has changed to 4.5, something like that. Now what I have shown on board, these are the velocities of a single fluid particle, not multiple fluid particle. These are the velocities of single fluid particle. Now the question arises is, sir, why these single fluid particle, the velocity is varying so much? The velocities are varying so much in this single fluid particle because there is huge order intermixing is there, collisions are there. So due to that, the velocity keeps on changing. So what scientists said was that for this huge kind of variation is there, you can find an average velocity. For example, let us say, just for the sake of example, let us say the average of all this is 4. Let us say that the average of all these velocities is, let us say, 4. Then they said any velocity, for example, if you want to write 4.5, for example, if you want to write 4.5, so therefore any velocity can be written as a combination of average plus the fluctuating part. Average plus the fluctuating part. For example, let us say you want to write 5.5. 5.5 can be written as 4 plus 1.5. For example, if you want to write 2.5, 2.5 can be written as 4 plus minus of 1.5. So therefore, any value can be written as a combination of average, and the average is not going to change throughout, okay? And this component part is known as the fluctuating component. This component part is known as the fluctuating component. So fluctuating component will keep on changing. Fluctuating component will keep on changing. Wonderful. Look here. So for example, it is something like this. Let us say I am plotting the velocity of a certain fluid particle. So the velocity of that certain fluid particle is going to vary something like this. Is going to vary something like this with time. Why there is so much of variation in the velocity of this fluid particle with time? Because first of all, the flow is unsteady. So this is another objective question is there. They will write a turbulent flow is, the answer is 100% guarantee it is an unsteady flow. It is an unsteady flow. So why these kind of variations are happening? Because collisions and intermixing is there now. If collisions and intermixing are there, for these variations, this center line which I have made here on the board, I am saying that this is the average component. I am saying that this is the average component of all the variation. You know, average component is shown by bar. So U bar represent average component. U bar represent average component. For example, let us say you want to write the velocity at this point. For example, let us say that you are writing velocity at this point. So if you are writing velocity at this point, the velocity at this point can be written as average plus the fluctuating component. Average plus the fluctuating component. So this U dash. So U bar symbol represents average and U dash symbol represents the fluctuating component of velocity. Represents the fluctuating component. Represents the fluctuating component. For example, let us say you want to write the velocity of this point. So if you want to write the velocity of this point beta g, then this is average velocity and you know this is the fluctuating component. This is the fluctuating component, but this time of course the fluctuating component will be 0. And see, if you people are engineers, at least you should be knowing this. The meaning of average is that all the things which are lying above this, all the values which are lying above this and all the values which are lying below this, the time average of all of them is going to be 0. The time average of all of them. For example, this means over a certain duration of time, if this is the average value, then over a certain duration of time, all the positive fluctuating components and all the negative fluctuating components, the summation is going to come out to be 0. Has to be there now, because if average is there, all the things which are above the average, below the average, in a duration of time, the summation is going to be 0. So therefore, one more objective question, the time average of fluctuating components of velocity is always 0. The time average of fluctuating components of velocity is always 0. Very good. Now next, very, very important point. When I was teaching you boundary layer theory, in boundary layer theory, I beautifully taught you that even in turbulent flow, there is a small layer close to the boundary and that small layer is always laminar. So I told you that there is a small layer which is close to the boundary, and this small layer is always laminar even in turbulent flow, and that layer is known as, do you remember? That layer is known as laminar sublayer. So already I have taught you in boundary layer theory that turbulent flow can never be 100% turbulent. A turbulent flow can never be 100% turbulent. Listen carefully. A turbulent flow can never be 100% turbulent, because always in a turbulent flow, close to the boundary, close to the pipe wall, always the flow is going to be laminar, and that layer is known as laminar sublayer. That layer is known as laminar sublayer. That layer is known as laminar sublayer. Very good. So beta, few things I have taught you. Whatever I have taught you is already written on your page number 207. So few things to notice is, there is huge order intermixing is there. Due to huge order intermixing, all the properties are going to change. Not only velocity re baba, all the properties. For example, if you want to write the velocity will be written as u bar plus u dash. If you want to write pressure will be p bar plus p dash, something like that. So always any property in turbulent flow is written as a combination of average component and the fluctuating component. Average component and the fluctuating component, any property in turbulent flow. Clear, my dear? Yes. Wonderful. So let me summarize whatever I have, main important points. See, in this chapter, it is my personal guidance to you that all those formulas where I will mark red star or all those formula where I will mark star, no need to do the derivation, no need to do anything else. Just remember those formulas. Even if you remember those formulas then this chapter will be automatically, chapter will be taken care for you. Okay, for the exam point of view. Otherwise, a lot of stuff I am going to tell you, and they are experimental. So therefore you have to remember. So the first important thing is, turbulent flow is always an unsteady flow. Second thing is, there is huge order intermixing of fluid particles is there. So that's why there is a huge order variation in the fluid properties is there. Due to this, scientists, what they said was, any property in turbulent flow can be written as a combination of average component and the fluctuating component. The time average of fluctuating component of velocity over a duration of time is going to be 0. And laminar sublayer region is a special region present in turbulent flow close to the boundary where the flow will always be laminar. So a turbulent flow is never 100% turbulent. Never 100% turbulent. Next thing that we are going to find is the shear stress in turbulent flow. But wait. Before teaching you shear stress, you write one point on page number 207. One point is missing. Acha, everybody knows that when you are going to get turbulent flow in a pipe, whenever the Reynolds number is greater than 4000. Again, this is also an objective question, and we all know this, that if Reynolds number is greater than 4000, then it is turbulent. If the Reynolds number is less than 2000, then it is laminar. Wonderful. Page number 207. At the top of page number 207, write one point with red pen. Write down the time average of fluctuating component of velocity. The time average of fluctuating component of velocity is 0. The time average of fluctuating component of velocity is 0. Time average of fluctuating component of velocity is 0. Chaliye, look here. Please kindly look here. Next we need to find out that what is the value of shear in turbulent flow. Very interesting. See, shear stress in turbulent flow, if I use my brain, engineering brain, then turbulent flow is never 100% turbulent. Turbulent flow is always a combination of laminar and turbulent. Yes or no? So therefore, tau turbulent can be written as a combination of tau turbulent can be written as a combination of shear due to laminar and shear due to turbulent. Because everybody knows that there will be laminar sublayer will be there. So there will be some shear which will be developed in the laminar zone also. So this shear which is due to laminar, you are going to find this shear close to the boundary, close to the pipe wall. At the moment we are studying with respect to pipe now, also in turbulent flow. Close to the pipe wall, you are going to find shear stress laminar. But what about turbulent? Turbulent shear you are going to find away from pipe wall. Away from the pipe wall. Very good. Now listen carefully. We have already studied shear stress in laminar flow. We already know the value of shear laminar. We already know the value of shear laminar. Yes or no? Yes, sir. The new thing for us is tau turbulent. Acha, see, laminar shear is created like this. This is laminar shear. But how the shear is created in turbulent flow? Very simple. See, for example, if this is one molecule is there, this is another molecule is there, when they intermix with each other or when they collide with each other, so when you collide with, aap kyun collide karenge ji? When the molecule collide with each other, they create shear over them. They create shear with themselves. So therefore, laminar shear and turbulent shear, both are going to be there. See, my dear students, this laminar sublayer region or the shear due to laminar or the laminar sublayer region will be present in only a very small region which is close to the boundary or close to the pipe wall. So what the scientists are saying that this plus this is the total shear in turbulent flow, but scientists said that as this layer is very, very small, as this laminar sublayer is very, very small, so we are going to neglect the shear due to laminar. We are going to neglect the shear due to I am not saying that the shear due to laminar is 0. No. I am saying we are going to neglect the shear due to laminar. We are going to neglect the shear due to laminar and only tau turbulent will be there. And as I already told you, how to find out tau turbulent? Through experiments. There is no other choice. So now listen carefully. Many scientists will come and they will give their own theory that according to their experiment, this is the value of tau turbulent. Okay, so now on the board I will give you the formulas of 3 scientists. Those scientists, what experiment they did, what was their result, what was the thing was there, and how they did the experiment. It is not required for us to know all this stuff. The only thing that is required for us is to remember the formula that at the end, according to their experiment and according to their theory, what formula scientists have given. Okay, so first scientist whose theory that we have to study, whose value we have to see, the name of the scientist is according to Bouziness. According to Bouziness. So there was a scientist with the name Bouziness. He did his experiments and research and gave the value of tau shear. He gave the value of shear due to turbulence. So from his experiment, he gave the value of tau turbulent. And he wrote the value as eta into du bar by dy. This was the result which Bouziness got. Beta, I haven't mentioned star over this equation. This means whether you remember or not remember doesn't matter. Because this theory was a failure theory. It didn't gain popularity. The theory that gained complete popularity, I will teach you at the third number. It was given by Prandtl, which you have to remember. That is the most important theory. But here he defined, it was his experiment, he defined eta as eddy viscosity. He defined eta as eddy viscosity. He defined eta as eddy viscosity. Very good. Look here. So, just you need to remember the equation. Okay, no details are required. Number 2. The second scientist which gave his theory according to his experiments about the tau turbulent, and all this stuff is experimental. So if you want to know, you have to remember. So according to Reynolds, yes, his theory was a bit popular. His theory was a bit popular in the field of turbulent flow. So according to Reynolds, he found it out from his experiments that the value of tau turbulent is given as rho u dash v dash. Is given as rho u dash v dash. Just look at the board. I'm marking stars over this. This means you have to remember this. I'm marking stars over this equation. This means you have to remember this equation. Rho u dash v dash, where u dash and v dash, where u dash and v dash are the components of velocity, are the fluctuating components of velocity in x and y direction. Are the fluctuating components of velocity in x and y direction. Excellent students of India. Are the components of velocity in x and y direction. Just look at the board, my dear students. These are also known as, there is a name given to this, these are known as Reynolds stresses. These are also known as Reynolds stresses. You know, actually Bouziness, he, with the help of this symbol eta, in his theory, actually he wanted to represent the Reynolds stresses with the help of eta. So sometimes in some of the standard textbooks, it is written that Bouziness theory is nothing, it is a representation of Reynolds stresses itself. But he failed to do that. He wanted to represent the Reynolds stresses in the form of his thing, that is eta, that is eddy viscosity, but he failed to do that. That's why this theory was a failure. But yes, Reynolds stresses were there. But then came a mind-blowing scientist, number third. His name was Prandtl. So according to Prandtl, beta, this complete theory I am marking star, so you have to remember. This complete theory I am marking star, so you have to remember. Now what Prandtl did was, Prandtl said that Reynolds have already given the value of tau turbulent as rho u dash v dash. Prandtl only found out the values of u dash and v dash. So Prandtl, from his experiments, he found out the values of fluctuating components of velocity in x and y direction. And he found out that the values of u dash and v dash was same. All these are experimental data and results. Unfortunately, you have to remember, I can't do anything. So from his experiments, he found it out that the value of u dash and v dash was coming out to be same, and that value he defined as L du by dy. L du by dy, where this L is known as mixing length. Where this L is known as mixing length. From his experiments, he defined the value of L as k into y, where y is the distance from pipe wall. It is the distance from pipe wall. And the value of k from his experiment, all these are experimental. मैं क्या करूं जी अभी, मैं कुछ नहीं कर सकता जी. एक्सपेरिमेंट है तो है, याद करना है तो करना है. जहां पर आपको मैं बता सकता था, wherever I could have told you things, wherever I could have made you feel the things, I have already done in the subject. But where you have to remember completely, then you have to remember, we don't have a choice. From his experiments, he found out the value of k as 0.4 for a pipe. He found it out the value of K as 0.4 for a pipe. Wonderful. So therefore, if we go by this logic, then you know tau turbulent, which was given by Prandtl, was rho u dash v dash. It was given by Reynolds, rho u dash v dash. But the value of u dash v dash was found out by Prandtl, na. So therefore, ultimately, what is rho u dash v dash, and the value of u dash v dash was found to be same. So it will become rho L square du by dy ka whole square. Oh my God, this is a very, very famous formula, and you have to remember this formula by heart. This formula for your GATE and ES examination. Twice in the ES examination, directly he has asked in the prelims paper, the shear stress for turbulent flow is given by. The shear stress in turbulent flow is given by. The answer is rho L square du by dy ka whole square. Now, one more very important question that is asked here is mainly interview question. Mainly interview question they ask is, what do you mean by mixing length? What do you mean by mixing length? Let me tell you what is mixing length. See, for example, if this is one layer of the fluid is there, this is another layer of the fluid is there. Now what actually happens in turbulent flow is, in turbulent flow, the molecule which is present in this layer, it is going to move and it is going to intermix with the another layer. This is known as turbulent flow, na? When the fluid particle are leaving their one layer and shifting to the another layer, intermixing. This is the meaning of turbulent flow, na? So the molecule which is present here is going to go and move into the another layer, and my question to you guys is, when this molecule was present in this layer, it was having the velocity, the properties, everything of this layer. But when it got intermixed into this layer, it will attain the properties of the new environment. But it is not going to attain the properties of the new layer instantaneously. It will take some time. So therefore, this molecule, it will take some time to attain the properties of the new layer. And you know, the distance traveled by the molecule up to the point where it attains the properties of the new environment is known as mixing length. For example, let me give you an example. For example, in Delhi, offline made easy class is there. Every year, a lot of students from outside states, they come into Delhi and they stay there and they do their coaching and stuff. So for example, you are coming to Delhi. Let us say you are coming from Haryana. Let us say you are coming from Uttar Pradesh. You are coming to Delhi. You are coming to Delhi for Made Easy coaching. Now when you come to the coaching, on the first day itself, when you enter Delhi and you take admission in Made Easy, on the first day itself, do you start to prepare? No. The answer is no. My dear students, for the first few days, let us say 2 to 3 days, first of all, you will try to find a room for yourself, hostel PG or something. There are a lot of hostel PGs are there surrounding Made Easy. So therefore, first of all, you will try to find a hostel or PG, something like that. Then you are going to purchase some basic stuff like a mattress or some table or things like that. A few things you are going to accumulate. Basic stuff. So this is going to take 2-3 days. After 2-3 days, when you are settled in Delhi, now your preparation will start. You will become apt to the new environment. And once you become apt to the new environment, then your efficiency increases. Similarly, there is a molecule is there which was present in one of the layers. That molecule got intermixed into another layer, but just as soon as it got intermixed, it will not take up the environment of the new layer. It will take some time. So in that time, that molecule is going to move by a further distance, let us say, with the new layer. So what is mixing length? The total distance traveled by the molecule up to the point where it attains the new environment is known as mixing length. Where it attains the new environment is known as mixing length. Very good. My dear students, all this thing rho L square du by dy ka whole square is already written in your printout, so no need to worry. But the definition of mixing length is missing in your printout. So please write down the definition of mixing length somewhere in your printout. Write down the definition of mixing length somewhere in your printout. Come to page number 212. Come to page number 212 of your printout. Come to page number 212 of your printout. Can you see that the complete page is empty? Can you see that the complete page is empty? Write down the definition of mixing length. Write down. Mixing length is defined as the distance traveled by the molecule. Mixing length is defined as the distance traveled by the molecule up to the point where it takes up the new environment. Up to the point where it takes up the new environment is known as mixing length. Where it takes up the new environment is known as mixing length. Where it takes up the new environment is known as mixing length. Where it takes up the new environment is known as mixing length. Wonderful. Look here. Hey, please, kindly look here. The next thing I want to find out is the velocity distribution. Here I have found it out, rho L square du by dy ka whole square. The next thing I want to find out is the velocity distribution in turbulent flow. Already somewhere in the subject, when I was teaching you laminar flow, I made a diagram that the velocity distribution in turbulent flow is going to be logarithmic. So now we are going to prove that. But wait, before proving that, one more new term I have to introduce here, and that is known as shear velocity. That new term, my dear students, is known as shear velocity. Shear velocity is shown by the symbol V star. See, shear velocity is a hypothetical thing. It's a fictitious quantity. I will tell you, don't worry. It is a fictitious quantity. Because in a lot of books, the methodology that is used to explain shear velocity, they use this term, fictitious quantity. It is a fictitious quantity. Fictitious means hypothetical. Hypothetical quantity. Acha. Now what is V star? To find out V star, we should start from our laminar. So if you remember, what was the formula for shear stress in laminar flow through pipes? In laminar flow through pipe, the shear stress formula was minus of del P by del X into R by 2. Del P by del R. Acha, it is changing in X direction. So minus of del P by del X into R by 2. Do you guys remember the formula for shear that I taught you in laminar flow through pipes? Yes. This was the formula. But if I want the formula in terms of, let us say, diameter. So if I want to convert this in diameter, so R will be written as D by 2. So if I want to write in terms of diameter, so tau can be written as minus of del P. See, del P will be P2 minus P1 divided by del X. Del X is X2 minus X1 into R by 2. R by 2 can be written as D by 4. My dear students, this can be written as, when you bring minus sign inside, this will become P1 minus P2. And how many of you remember that P1 minus P2 by W? P1 minus P2 by W is equal to head loss. So P1 minus P2 can be written as W into head loss. Do you remember all this stuff I have already taught? So when you bring minus sign inside, it will become P1 minus P2. And P1 minus P2 is equal to W into head loss. P1 minus P2 will become W into head loss divided by X2 minus X1 is L. Arre re Baba. If you remember the last derivation of laminar flow through pipe, we took a pipe something like this. This was 0.1, this was 0.2. The distance from here was x1, the distance from here was x2, the distance between these 2 points was L. So I am using the same diagram. So x2 minus x1 can be written as L, and this will be 4L multiplied by D. Now look here. So shear stress can be written as, so therefore, wonderful, but. So therefore, you know, my dear students, here we are going to find the wall shear stress. Actually, we are interested in what? We are interested in wall shear stress. So some students, they might be having a doubt that, sir, why you have converted this small r in terms of capital D? Because capital D is the complete diameter of the pipe. How you have converted small r into capital D, sir? We are using a condition now for wall shear stress. What is that condition? At r is equal to capital R, tau will be equal to tau naught, or the wall shear stress. So when you put r is equal to capital R, here capital R will be there, and now capital R, when you convert to diameter, it will be d by 2. So this is wall shear stress. This is wall shear stress, my dear students. This is wall shear stress. So wall shear stress, W can be written as rho into G into head loss is FLV square by 2GD. FLV square by 2GD into D divided by 4L. So D and D is cancelled out. L and L is cancelled out, and G is also cancel out. 2 into 4. This is a very important formula. This is a very, very important formula. You have to remember this. So wall shear stress is given as rho FV square by 8. Oh my God. So you have got a direct formula for wall shear stress. You have got a direct formula for wall shear stress. So from today onwards, if anybody asks you, find the wall shear stress, this is your direct formula. So wall shear stress is rho FV square by 8. But don't take it lightly. In few of the PSUs, and I think in 2017, Engineering Services prelims paper, mechanical engineering only, he asked, the wall shear stress is given as ABCD option. This was the correct option. This was the correct option. Clear, guys? Yes, look here, look here. Please look here. So rho FV square by 8. But the most important thing is, this formula is applicable to laminar as well as turbulent flow. Oh my God, very important point again. This formula of wall shear stress is applicable to laminar as well as turbulent flow. Now the student is in a state of confusion. Student will say, sir, you started this to find this formula by laminar equation. This was a laminar flow equation. But now why the hell? Because you started with a laminar equation and now you are saying that this formula is applicable to laminar as well as turbulent, sir? How it can happen, sir? How it can happen, sir? Because you are saying laminar and turbulent, both it is applicable. Kya karte ji aap log? Why? Can anybody in the comment box tell me why I am saying that this formula is applicable to laminar as well as turbulent? Come on. Tell me in the comment box. Anyone who can use his brain. Anyone who can use his brain, why I am saying that this formula is applicable to laminar as well as turbulent. You know, even in turbulent flow, the region close to the boundary is laminar itself, and what you are finding, wall shear stress. So if you will see at the wall, no matter whether it is laminar, no matter whether it is turbulent, at the wall the flow is laminar only. Hence this formula is applicable even to turbulent flow. Yes, very good. Very good. Every one of you is giving the correct answer. I'm very happy. I'm very happy that all of you are giving the correct answer. See, look here. Look here, everyone. Now student will say, sir, okay, you have found out the value of tau naught. Yes, very good, very good. All of you are giving the correct answer. I am very happy. All of you are alive. Idhar dekho. Now student will say, sir, you have to find out shear velocity. But you have found out this. My dear students, now I will define shear velocity. Shear velocity, which is V star, shear velocity V, which is V star, is defined as under root of tau naught by rho. So tau naught is there, rho is there, do the under root of this. Tau naught is there, rho is there, do the under root of this. So if you do the under root of this, this is going to be under root of f by 8, and v square under root will be v. V square under root will be v, and this, my dear students, is shear velocity. Very, very important. Very, very important. Now some students will say, sir, what is the relevance? Some students will say, sir, what is the relevance of all this stuff? Dekho. This V star, there is no relevance. That is the reason why we are saying it is a fictitious quantity, na? There is no relevance. That is the reason why we are saying it is a fictitious quantity. Okay? Then student will say, sir, why are you defining it if it doesn't have any significance? See, this term, which is tau naught by rho under root of tau naught by rho, under root of tau naught by rho, under root of tau naught by rho, this particular term was repeating again and again in the derivations of turbulent flow. So just for the sake of simplicity purpose, scientists said that this complete term under root of tau naught by rho will be written as V star. This complete term under root of tau naught by rho will be written as what? V star. Are we clear, beta? Yes. Just for example, the term mu by rho, mu by rho, mu by rho was again and again it was getting repeated. Which term? Mu by rho, mu by rho, mu by rho. This term was again and again getting repeated in our derivations. So scientists said that if this term was repeating again and again, let us take it to be as a new term, which is kinematic viscosity, helpful in our calculation. In the same manner, in turbulent flow derivations, this term was getting repeated again and again in our derivation. That's why they took it to be V star. And the value of this we can find from here, is under root of f by 8 into V. This is a very, very important formula. Mark stars in your printout also. Mark stars in the printout also. Mark stars in the printout also. Now look here. Let us go for velocity distribution. Already I know that the velocity distribution will be logarithmic, but still let us find out that. So everybody knows tau is equal to rho L square du by dy ka whole square. This is the shear stress in turbulent flow. So what you are going to do is du by dy ka whole square can be written as tau by rho into 1 by L square. Do the under root of this. So du by dy is equal to under root of tau by rho into 1 by L. My dear students, let us integrate this. So when you are going to integrate this, you will come out to be, see, under root of tau by rho. Just now I told you under root of tau naught by rho can be written as V star. So therefore this can be written as V star divided by L. Divided by L, and L according to Prandtl was K into Y. Come on guys, L according to Prandtl was K into Y, and K value you are going to take as 0.4. So 1 divided by 0.4 will be 2.5. 2.5 of V star by Y. अभी इंटीग्रेट नहीं कर रहे हैं, यहाँ पर du by dy ही रहने दो, ठीक है. So 2.5 V star. So from here the value of du can be written as, see, 1 divided by 0.4 is 2.5 of V star divided by y, into dy. Very good. So if you want to find the velocity, just integrate. U will be equal to 2.5 of V star 1 by dy by y integration is log y plus c. Oh my god, this proves that the velocity distribution in turbulent flow is logarithmic. You can clearly see from the equation. And this is the reason why This is the reason why if in a pipe, if you want to show the velocity distribution of turbulent flow, the velocity distribution of turbulent flow, my dear students, is logarithmic. So please remember this for objective paper. Please remember this for objective paper. And you can also remember this equation also, just for the sake of security purpose, nothing else. Okay? Yes. It is logarithmic. It is logarithmic. Now let us move on to the most important topic of this chapter. Because you know, generally most of the questions which are asked in this topic, they are asked from this topic, which I am teaching now. So there are two types of, please, this is a serious topic. You know, there are two types of pipes are there, hydrodynamically. One is known as smooth pipe. One is known as smooth pipe and one is known as rough pipe. One is known as smooth pipe and one is known as rough pipe. Look here on the board. See, for example, beta, please concentrate on board. This last topic. Yes, turbulent flow is over after this. Few more equations, one or two equations I will tell you. Turbulent flow is over after this. So this is the last most important topic of this chapter, from where maximum time the questions are asked. Look here. For example, if you will look at your pipe surface, now for example, let us say this is the pipe surface is there. Then in the pipe surface, always there are going to be small irregularities or roughness is going to be there on the pipe surface. So when you are going to zoom this pipe surface, for example, if there is this pipe surface is there, and with the help of microscope, you are zooming into that pipe surface. So when you are going to zoom into that pipe surface, no matter how much good surface finish you do, no matter how much better device you make or better pipe you make, 101% always at microscopic level, whenever you see, you are going to find irregularities on the surface of the pipe, roughnesses on the surface of the pipe. So for example, let us say this is our pipe is there. For example, let us say this is our pipe is there, and if let us say this is our pipe is there, pipe surface is there, then if you will see on microscopic level, there are going to be irregularities over the surface of the pipe. So this is, beta, can you imagine we are saying at microscopic level? So try to imagine in that sense that this laminar sublayer height is not going to be very large. It will be a very small minor layer will be there. Okay. So therefore this white color thing that I am showing is irregularities over the pipe surface. For example, here also at microscopic level, if you will see the pipe, you are going to find the irregularities. Now listen carefully. If you are talking about turbulent flow, everybody knows that near the pipe wall in turbulent flow, the flow is laminar. Near the pipe wall in the turbulent flow, the flow is always laminar. So for example, if this is your pipe wall is there, and near this pipe wall, there is going to be a certain region or there is going to be a certain height up to which the flow is from the pipe wall up to that certain height, the flow is going to be laminar, and that layer is known as laminar sublayer, and the height of that layer is shown by the symbol delta dash. The height of that layer is shown by the symbol delta dash. Now what is delta dash? Delta dash is nothing, it is the height of laminar sublayer. It is the height of laminar sublayer. And you know, the height of laminar sublayer was given by a very famous scientist which is 11.6 nu by V star, is known as the height of laminar sublayer, again coming from experiments, and this value was given by a very famous scientist in the field of turbulent flow. His name was Nikuradze. And this equation is purely based on experiments. So Nikuradze, he did a lot of experiments, and from his experiments he found it out or given an expression for the height of laminar sublayer. So height of laminar sublayer is 11. This is a very, very important formula. 11.6 nu by V star. 11.6 nu by V star. Where what is V star? V star is under root of tau naught by rho is equal to under root of f by 8 into V. Is under root of f by 8 into V. Clear, guys? Yes. Very good. Now look here. So if this height is delta dash, can you see that delta dash height is not fixed? It will change from flow to flow. What a wonderful thing, यार. देखो भैया, ये जो delta dash है, this is going to vary. This is going to vary with flow to flow. For example, if you change the velocity of the flow, the V star will change. V star changes, delta dash changes. If you change the friction factor, if you change the kinematic viscosity of the flow, therefore the value of delta dash or the height of this laminar sublayer is dependent on the flow, not on the pipe surface. Please try and understand this. So what actually your teacher wants to say here is, for example, let us say I am having a pipe. In that particular pipe, the value of delta dash, will it be always fixed or that pipe? The answer is no. The value of delta dash will keep on changing from flow to flow. So the value of delta dash is never ever fixed in a pipe. It keeps on changing from flow to flow. For example, in a certain pipe, let us say at the moment water is flowing in that pipe. Let us say at some other moment, some other fluid is flowing in that pipe, the value of delta dash will change accordingly. So value of delta dash depends on the flow. For example, look here. And what is the next thing I should define is K. K is known as height of irregularity or height of roughness. So what is K? K is the average height. K is the average height of roughness, or irregularity. तो बच्चों इधर देखो, ये जो पहाड़ नुमा इरेगुलरिटीज बन रही है, सफेद इरेगुलरिटीज तो है, तो ये जो पहाड़ नुमा इरेगुलरिटीज बन रही है, इन्हीं का हाइट क्या दिखाता है? के सिंबल इनका हाइट दिखाता है. सो द हाइट ऑफ दीज इरेगुलरिटीज इज शोन बाय द सिंबल के. नाउ व्हाट इज अ स्मूथ पाइप? अच्छा, लिसन. The value of K is dependent on the pipe. So the value of K for a given pipe will be fixed. But the value of delta dash will keep on changing from flow to flow. Can you understand that? For example, if I am having a certain pipe, then the K value is fixed. But the delta dash value will keep on changing depending from flow to flow. Now comes the beauty. If in a certain case delta dash is very, very greater than K, then such a pipe is known as a smooth pipe. So whenever in a fluid flow, the height of the laminar sublayer, if the height of the laminar sublayer is greater than the height of irregularities, always that flow is going to be smooth pipe. Matlab that pipe is called as a smooth pipe. Now why this is called as a smooth pipe? Look here. if the height of laminar sublayer is greater than the height of irregularities, then this is the laminar sublayer. Above the laminar sublayer, there is going to be irregular flow is going to be there, turbulent eddies and everything is going to be there. Yes or no? Yes, sir. And if there are irregularities are there, turbulent eddies and everything is there, then my dear students, all these turbulent eddies and irregularities, there is a laminar sublayer. So those, they are not, वो लोग इसको तोड़ नहीं पाएंगे laminar sublayer को. So therefore they will not be able to break the laminar sublayer and strike with the irregularities. Because who is guarding the irregularities? Laminar sublayer. So laminar sublayer in this particular case is acting as a shield to the turbulent eddies. And the turbulent eddies are not able to strike with the irregularities. Such a pipe is known as a smooth pipe. Such a pipe is known as a smooth pipe. Then what will be a rough pipe? Rough pipe will be opposite of this. Opposite of this means that the height of laminar sublayer is very less. Opposite of this means that the height of laminar sublayer is very, very less. If the height of laminar sublayer is very, very less in comparison to the height of roughness, so therefore the turbulent eddies will be able to strike with the roughness, and such a pipe is known as a rough pipe. So whenever K value is very, very less than delta dash, whenever K value is very, very greater than delta dash, K value is greater than delta dash, then the roughness height is greater than that. My question to you, and you, each and every student has to tell me in the comment box. Each and every student has to tell me in the comment box the answer to this question. My question to you. For example, at the moment I am having a pipe, and that pipe is behaving as a smooth pipe. Okay? My question to you guys is, will that pipe, which is at the moment smooth pipe, will that pipe always behave as a smooth pipe? Tell me in the comment box, yes or no. Tell me in the comment box, yes or no. एक बारी हिंदी में बोल देता हूँ, अगर कोई एक ऐसा पाइप है जो कि अभी स्मूथ है, क्या वो हमेशा स्मूथ ही रहेगा? क्या वो हमेशा स्मूथ ही रहेगा? No, it is not mandatory that it will remain smooth. Because see, for a certain pipe, at the moment if he is behaving as a smooth pipe, this means delta dash was greater than K. But if you change the flow, it can happen that delta dash can fall below the K for the same pipe. So the same pipe under a certain flow can behave as smooth, same pipe under a certain flow can behave as rough. Very good. Yes. Everyone is correct. So from today onwards, if in any examination he is asking you what is smooth and rough, something like that, you can give the answer. Look here. See, just like studying the definition of laminar and turbulent is a different thing, but bifurcating both of them mathematically is a different thing. है ना? So therefore studying turbulent flow is a different thing. Studying laminar and turbulent flow definition is a different thing, but bifurcating them based on a formula is a different thing. What is used to bifurcate them? Reynolds number. In the same manner, studying the definition of smooth and rough pipe in turbulent flow is a different thing, but bifurcating them mathematically is a different thing. So there were two scientists were there. Very, very important. There were two scientists were there. Which two scientists, beta? The name of the first scientist I already told you. The name is Nikuradze. The name of the first scientist I have already told you. The name of the scientist is Nikuradze. And the second scientist who gave his theory was Reynolds. Now what both of them did was, from their experiments, they gave the value. They gave some terminology that below this pipe will behave as smooth, or above this the pipe is going to behave as rough. Above this pipe is going to behave as rough. Very good. So Nikuradze, what he gave was that if the value of K by delta dash is less than 0.25, the pipe is treated as a smooth pipe. If the value of K by delta dash, is less than, let us say 6, and between 0.25 and 6, this is transition. Transition means you cannot decide whether it is behaving as a smooth or rough. If the value of K by delta dash is greater than 6, then it is treated as a rough pipe. If the value of K by delta dash is greater than 6, it is treated as a rough pipe. Wonderful. So, just like that you have remembered the Reynolds number, na? In the same fashion you have to remember this also. These you have remembered, na? That Reynolds number less than 2000 is laminar, greater than 4000 is turbulent. You have remembered the value, na? And you have also remembered the Reynolds number, rho v d by mu. In the same manner you have to remember these values, because in the numerical he is going to ask, tell whether the pipe is a smooth pipe or rough pipe. Then very simply what you find out, K by delta dash. If the value of K by delta dash for your pipe, is less than 0.25, it is treated as a smooth pipe. If it is between 0.25 and 6, it is treated as transition. And K by delta dash, if it is greater than 6, it is treated as a rough pipe. Are we clear? Yes. But wait, there was one more scientist was there, Reynolds. Reynolds is such a, मतलब क्या गजब के साइंटिस्ट रहे हैं यार. इन्होंने लेमिनार और टर्बुलेंट को बाइफरकेट करने के लिए आपको बताया, और साथ ही साथ स्मूथ और रफ पाइप को भी बाइफरकेट करने के लिए आपको विज्ञान दिया. So Reynolds was such a scientist, he beautifully bifurcated between laminar and turbulent with the help of Reynolds number. But he also did experiments and bifurcated between smooth and which pipe will be smooth and which pipe will be rough. And he gave a number here known as Reynolds roughness number. He gave a number here known as the Reynolds roughness number. Now what is Reynolds roughness number? Reynolds roughness number is defined as V star K by nu. बेटा यू हैव टू रिमेंबर, जैसा आपने रेनॉल्ड्स नंबर याद कर रखा है वैसे ही आपको रेनॉल्ड्स रफनेस नंबर भी याद करना पड़ेगा. मैं क्या करूं जी, अब इस चैप्टर में याद करने का है तो है, क्या करूं जी मैं, बताओ आप. सो यू हैव टू रिमेंबर V star K by nu. You know, whenever the value of V star K by nu or the Reynolds roughness number, if that value is less than 4, then the pipe is treated as a smooth pipe. If the value of V star K by nu is less than 104, if it is between this range, it is treated as transition. And if the value of V star K by nu is greater than 100, it is treated as a rough pipe. Now student will ask me, sir, if in any examination, if someone is asking us, tell whether the pipe is a smooth pipe or rough pipe, sir, which one I should use? Whether I should use the Nikuradze or whether I should use the Reynolds hypothesis? Beta, you use anything. Answer will be same. For example, if you solve by Nikuradze and Nikuradze is giving that the answer is smooth pipe. If it is Nikuradze and he is giving that the answer is a smooth pipe, then you know Reynolds will also give that the pipe is a smooth pipe. There is no doubt in that. Reynolds will also give that the pipe is a smooth pipe. Excellent, bachcho. Excellent. On page number 2, all this stuff, whatever I am teaching, is already written in your printout. But one thing is missing. On page number 210, On page number 210 of your printout, beta, write this, the definition of delta dash and k. Please write this. Please write this on page number 210. Write this definition of delta dash and k. Come on, come on, come on. Write down the definition of delta dash and k. Very good. Very good. Done? Wonderful. Chalo, idhar dekho. My dear students, now let me tell you the velocity distribution equation which is written on page number 211 on your printout. There is a velocity distribution equation is there. What is that equation? U minus V by V star is equal to 5.75 log base 10 y by r plus 3.75. The famous velocity distribution equation for turbulent flow through a circular pipe. You know this equation. There is a derivation to this equation, but even in that derivation, you use the experimental data and experimental results. So no need to derive this equation. First of all, your question will be, sir, do we need to derive this equation? The answer is no. Directly remember this equation, but this equation is also when you are going to derive this equation, in this equation also experimental data will be utilized. In this equation also experimental data will be utilized. Okay, so but you have to remember this. Okay, now just look at your printout. Just look at your printout on page number 211. On page number 211, can you see friction factors of turbulent flow? Yes, sir. Unfortunately, my dear, you have to remember this also. These friction factors was given by a scientist with the name Moody's. These friction factor was given by a scientist with the name Moody's. So Moody's, he actually made a chart. He actually made a chart. And what your teacher has done is, for your safety purpose, I have already taken out the values from that chart. And I have put it in the form of a table, something like this. But it's just look at here. Friction factor of smooth pipe is different. And friction factor of rough pipe is different. Unfortunately, I can't help it. You have to remember these friction factor values. Okay, this was given by Moody's. So all these are experimental stuff. All these are experimental stuff. Do you remember the friction factor of laminar flow 64 by Reynolds number? It was so easy. But to remember the friction factor of turbulent flow, you will have to remember, unfortunately. And you know, for smooth pipe and rough pipe, the values are different and they come from experiments. Like we did that 64 by Reynolds number, we derived that in laminar flow. But in turbulent flow, friction factors comes from experiments. Chaliye, now we are going to solve some numericals. Even in this small chapter, you will find that I am going to solve so many variety of numericals. And once you solve numericals, then only you will gain the strength that yes, sir, we are understanding. Yes, sir, we are understanding. Yes, sir, we are understanding. But before starting the numericals, tell me in the comment. See, in this chapter, most of the things you have to remember. Okay, so, but still, you tell me in the comment box whether you have understood something. Whether you have understood something, tell me in the comment box. Chaliye, let us now solve some numericals. Let us now solve some numericals. Let us now solve some numericals. Come to the question bank of boundary layer theory. Come to the question bank of boundary layer theory. Come to the question bank of boundary layer theory. Very good. Chaliye, let us start with question bank question number 1. Let us start with question bank question number 1. Don't worry. When we will solve the numericals now, you will gain a lot of confidence. When we are going to solve numericals, of course V star will change. Look here. Show that for turbulent flow through pipe, the ratio of maximum velocity to average velocity. So he is asking that for turbulent flow through pipe, you have to prove something. What you have to prove? You have to prove that Umax by V is equal to 1 plus 1.33 of root F. You have to prove for turbulent flow that Umax by V is 1 plus 1.33 of root F. You have to prove this for turbulent flow through pipe. Do you remember this value was written somewhere in the summary table in your laminar flow? Because in laminar flow we also found it out the value of Umax by V for laminar flow through pipe was 2. The value of Umax by V for laminar flow between parallel plates was 3 by 2, 1.5. And in that table itself I wrote that the value of Umax by V for turbulent flow through pipe is this, and now I am proving that. Look here. How to prove this? See, for proving this we have to use the velocity distribution equation. There is only one velocity distribution equation is there in turbulent flow. What is that equation? U minus V by V star is equal to 5.75 log base 10 y by r plus 3.75. U minus V by V star is equal to 5.75 log base 10 y by r plus 3.75. But wait, you don't, to prove this, you don't want U, you want U max. Now how to convert this into U max? At y is equal to r. Y is the distance from pipe wall. Arey, why don't you understand? This is center line of the pipe now. So at y is equal to r, it will be center line where the velocity will be Umax. At y is equal to r will be center line now, velocity will be Umax. So at y is equal to r, u will be equal to Umax. At y is equal to r, u is equal to Umax. So therefore, let us put it here. So in place of u, I will put Umax minus v by v star is equal to 5.75 log base 10 y by r. In place of y, you are going to put r. So r by r. R by r is 1. Okay. Plus 3.75. Plus 3.75. Plus 3.75. R by r is 1. Log base 10 1. Acha. Hey. Listen. Don't forget, because a lot of students they commit silly mistake here. In this particular formula, this is not log base e, this is log base 10, okay? Because generally we are having a habit of using that. So therefore log base 10 of 1 is 0. So this term is gone. If this term is gone, my dear, then what is remaining? Umax minus V. Umax minus V is equal to 3.75 of V star. Umax minus V is equal to 3.75 of V star. Wonderful. So from here, let us find the value of Umax. So Umax is going to be 3.75 of V star plus V. 3.75 of V star plus V. I'm getting closer. So let us divide. I need to find Umax by V. So Umax by V is going to be what? So let me divide by V. So Umax by V will be 3.75 of V star by V plus 1. 3.75 of V star by V plus 1. Hey, listen. V by V will be 1 now. Look here. Do you guys remember just few minutes back I told you that V star is under root of F by 8 into V. Arey Baba, shear velocity formula. I've already told V star is under root of F by 8 into V. So from here, let us find the value of V star by V. V star by V will be under root of F by 8. V star by V will be under root of F by 8. When you put under root of F by 8 in this equation, you are going to get the value that U max by V is 1 plus 1.33 of root F. Proved. Proved. And once it is proved, can you use this formula for solving numericals? Yes. So from today onwards, you can use this bloody formula in solving the numericals. Other numericals also, yaar. So therefore, what is the value of U max by? So again, I am making you revise. You know why I am so happy? I'm so happy because when I was teaching you laminar flow, I promised you that I will derive this. And today I have kept my promise. That's why I am happy. So therefore, you know, U max by V for laminar flow through circular pipe is 2. U max by V for laminar flow between parallel plates is 3 by 2, 1.5. U max by V for turbulent flow through pipe is 1 plus 1.33 of root F. Is 1 plus 1.33 of root F. Look here. One more promise I am telling. Look here. So I am writing one question here on board. Find the location where U is equal to V for turbulent flow. Find the location of the point where U is equal to V. Find the location of the point where U is equal to V for turbulent flow. Where U is equal to V for a turbulent flow. My dear students, this same variety of question already solved in laminar flow. In laminar flow, we found out the location of such a point where the local velocity becomes equal to average velocity. You can check your notes also. The answer was 0.707 of R. अरे यार कैसे students ये लोग revise ही नहीं कर रहे हैं. The answer was 0.707 of R. Was the location of the point in laminar flow where the local velocity becomes equal to average velocity. But this time, same thing we are going to find in turbulent flow. This time, same thing I am going to find in turbulent flow. Look here on the board, my dear students. So therefore, again we have to start from the velocity distribution equation. U minus V by V star is equal to 5.75 log base 10 Y by R plus 3.75. See, he is asking us for a location of a point where U becomes equal to V. So LHS becomes equal to 0. If LHS becomes equal to 0, this is minus of 3.75 is equal to 5.75 log base 10 Y by R. Wonderful. So this will be written as minus of 3.75 divided by 5.75 is equal to log base 10 Y by R. You need to find out the value of R. For finding the value of R, you have to remove this log. For finding the value of R, for finding the value of Y, you need to remove this log. So how to remove the log? Take it to that side. It will become 10 to the power. Remember, this is not log base E, this is log base 10. So it will be 10 to the power. So Y by R will be 10 to the power minus 3.75 divided by 5.75. Divided by 5.75. So from here, when you are going to calculate the value of Y, it will come out to be 0.223 of R, and that's our answer. So kindly remember for objective paper, mere lal. Let me make a summary. Otherwise, you are not going to take it seriously. Let me make a summary. This is a summary of what? This is a summary when U becomes equal to V. This is a summary when U becomes equal to V. Okay. So for laminar flow through pipe, the location of the point where U becomes equal to V is actually R is equal to 0.707 of R. And for turbulent, my dear students, Y is equal to 0.223 of R. Y is equal to 0.223 of R. Are we clear? Yes, sir. Please remember this. Just the only thing to notice here is this is the distance from center of the pipe. This is the distance from the pipe wall. Please remember for objective paper. Next, let us go for question number 2. Question bank, question number 2. Question bank, question number 2. What is the question? A pipe carrying water has average height of roughness. See, I am only going to give you hint to these questions. Calculations you have to do by yourself. A pipe carrying water. So there is this pipe is there in which you are carrying water. Has average height of roughness. Average height of roughness is K. K is the height of roughness, na? K is 0.48 mm. 0.48 mm. The diameter of the pipe is given to be as 0.68 meter. The length of the pipe is given to be as 4.5 meter. Discharge is given to be as 0.6 meter cube per second. Then he says, find the power required. Again in laminar flow, already beautifully taught to you the formula for the power required. To maintain the flow, if the viscosity of water is 10 to the power minus 3 Newton second per meter square, assume the pipe to be a rough pipe. My dear students, I am not saying that it is a rough pipe. It is already given in the problem that it is a rough pipe. Now listen carefully. For solving this kind of a problem, everybody knows that power formula is WQ into head loss in the pipe. Beta already taught in the laminar flow. The power formula is WQ into head loss of the pipe. W, you know, it is water. Discharge is given in the question. What is missing? Head loss. Head loss is missing. But wait. This value of head loss is FLQ square by 20 to the power 5. No matter whether your flow is laminar or turbulent, the value of head loss remains the same. See, the length of the pipe is known, discharge is known, 12 is known, diameter is known. What is missing? F is missing. F is missing. Now just wait. Friction factor depends on whether your flow is laminar or whether your flow is turbulent. If your flow is laminar, then friction factor will be 64 by Reynolds number. If your flow is turbulent, then friction factor will depend on whether your pipe is smooth or whether your pipe is rough. But wait, in the complete question, nowhere it is written or mentioned that the flow is turbulent or laminar. So the first step of this question is you should check Reynolds number. Yes. Because nowhere it is written that it is laminar or turbulent. So just by you can't आप सिर्फ assume नहीं कर सकते हो, आपको निकालना पड़ेगा. So Reynolds number, how you are going to find out? Rho VD by mu. Rho you know it is water, diameter you know, viscosity you know, velocity you know. How you will find the velocity? Everybody knows discharge is area into velocity. So from here you can find discharge, velocity is discharge upon area. So once you will find the Reynolds number from here, beta calculation you have to do, concept I am telling you. So Reynolds number, when you are going to find from here, you will find that the Reynolds number will come out to be greater than 4000. So if the Reynolds number comes out to be greater than 4000, proving that our flow is turbulent. Now if your flow is turbulent, the friction factor depends on two things, whether your pipe is rough or whether your pipe is smooth. But we need not find, because this is mentioned in the problem that the pipe is a rough pipe. So in a turbulent flow, if your pipe is a rough pipe, the friction factor will be given by Moody's equation, which were already mentioned in your printout. So what is the Moody's equation? 1 by root f is equal to 2 log base 10 R by K plus 1.74. This is the equation of friction factor for rough pipe. This is the equation for friction factor for rough pipe. Wait. A lot of students will do a silly mistake here. Now what is the silly mistake? The silly mistake that most of the students are going to do here is in the units of R and K. See, diameter is given in meter and K is given in mm. So please, diameter first of all divide by 2 to find radius. Either put both of them in meter or either put both of them in mm. I don't have any problem. But put in any single unit, either meter, either mm. Either meter, either mm. Now from here, only one unknown is there, which is friction factor. Find the value of friction factor, put in this, find the value of head loss. Once you find the value of head loss, put in this, find the value of power. Very good question. Very good question. Acha, can the same question be asked for laminar? Can the same variety of question can be asked for laminar in the paper? The answer is yes. Just all the steps will remain the same. The only difference will be, in place of this equation, you will use 64 by Reynolds number. That's it. In place of this equation, you will use 64 by Reynolds number. You will use 64 by Reynolds number. Wonderful. Let us go for question bank, question number 3. Let us go for question bank, question number 3. What he says? A rough pipe. So again in the question he has mentioned that the pipe is a rough pipe. Diameter of the pipe is given to be as 0.1 meter. Carries water at the rate of, this means discharge is given. Discharge is given to be as 50 liter per second, which can be written as 15 to 10 to the power. The height of roughness is given to be as 0.15 mm. Then find. A lot of things he is asking in the question. Very good. But again, I think water is flowing in this pipe. Yes, carrying water. Clearly it is written in the question that the pipe is carrying water. Now see, again, water. For water, the viscosity everybody knows is 10 to the power minus 3 Newton second per meter square. Beta, water is a very simple thing, na? Water density is 10 to the power 3. Viscosity is 10 to the power minus 3. This is kg per meter cube. This is Newton second per meter square. है ना? Wonderful. So what will be the first step? The first step will be check Reynolds number. Check Reynolds number. Just for your safety. I know it is turbulent. But just for your safety, check Reynolds number. How will you check Reynolds number? Reynolds number will be simply rho VD by mu. See, discharge is given. So from the discharge, you can find the velocity as discharge upon area. So put it in this. Okay. So Reynolds number will come out to be greater than 4000. So proving that the flow is turbulent. Clear? Now what you need to find out in the first part of the question? Friction factor. Beta, it is clearly mentioned in the problem that the pipe is a rough pipe. If it is a turbulent flow and the pipe is a rough pipe, the friction factor will be 1 by root f is equal to 2 log base 10 R by K plus 1.74. Again, don't do a silly mistake. Put the units of both of them in mm or put the unit of both of them in meter. Doesn't matter to me. So from this particular equation, can you find the value of friction factor? Yes. We can find the value of friction factor. Number 2. The second thing he is asking in the paper is shear stress at the pipe surface. To find the shear stress at the pipe surface, even in turbulent flow, there is a direct formula. Today only I told you the direct formula. Wall shear stress is rho FV square by 8. Rho FV square by 8. Friction factor you know, density you know, velocity you can find from here, divided by 8. Can you find the value of shear stress? Yes, number third part. In the third part, he is asking you shear velocity. In the third part, he is asking you shear velocity. So what is the value of shear velocity? Shear velocity is V star will be under root of tau naught by rho. It's over. Dekho, tau naught value you have already found out. Rho value you know it is water. Can you find the value of V star? Yes sir. Hey, don't take it lightly, Baba. This question came for 8 marks in Engineering Services mains paper. This question has been asked in GATE. The same question has been asked in Civil Engineering GATE paper. Also, this variety of question has been asked in mains paper for 7 marks. So, all the quality questions I am solving. Number 4th. What is the 4th part? You need to find maximum velocity. In the 4th part, you need to find maximum velocity. How will you find there should be a smile on your face, because just now I have proved that for turbulent flow, U max by V is 1 plus 1.33 of root F. Friction factor, you have already found it out. U max you need to find out, average velocity you have. So from this particular equation, can you find the value of U max? Yes sir. Very good sir. Yes sir. Very good sir. Bahut umda sir. Yes, we can find the value of friction factor. So see, let me solve one more problem. Chapter number 7 workbook. Chapter number 7 workbook. So this is chapter 7 of workbook, question number 8. Chapter 7 workbook, question number 8. No. This is not that question. This you can do. This is this is not that problem which I was thinking. This is question number 15. So chapter 7 workbook, question number 15. The velocity measurement of flow through a rough circular pipe. See, now in this kind of a question, you cannot find Reynolds number. But you have to gauge just by looking that rough circular pipe is saying. You just listen to me. When I was teaching you laminar flow, was there any concept like rough or smooth in laminar flow? The answer is no. So if in any question smooth or rough, if these kind of things are written in the problem, you should gauge from the problem itself that he is talking about turbulent flow. So therefore the velocity measurement to a rough circular average velocity is 2.6. So average velocity is 2.6 meter per second. Center line velocity means what? U max. So U max is given to be as 3.17 meter per second. He is asking you the friction factor. So clearly in the question it is mentioned that it is a rough pipe. Or very simply it's a rough pipe, so therefore indicating that the flow is turbulent. If the flow is turbulent, directly you can use U max by V is 1 plus 1.33 of root F. So U max you know, V you know. Can you find the value of friction factor? Yes, you can find. Let us go for workbook chapter number 7, question number 17. Workbook chapter number 7, question number 17. Look here. The flow of water having itna, so therefore which fluid is flowing beta ji? Water is flowing. Having density itna, kinematic viscosity is 10 to the power minus 6 meter square per second. In a commercial pipe having roughness, 0.12 mm, yields a shear stress at the pipe wall. So shear stress at the pipe wall is given to be as 600 Pascal. Then he is asking you to find out the value of K by delta dash. He is asking you to find out the value of K by delta dash. This question was asked in mechanical gate paper. Listen. It's a turbulent flow through pipe. So therefore he is asking you the value of K by delta dash. So let us find the value of K by delta dash. The value of K is already given, 0.12 mm. 0.12 mm, put it in meter, 0. Into 10 to the power minus 3, divided by delta dash. Delta dash you don't know. Let us find out. Delta dash is given by Nikuradze equation. Delta dash is given by Nikuradze equation. 11.6 nu by V star. The value of kinematic viscosity is already given to you. So this is 11.6 into 10 to the power minus 6 divided by V star. V star is what? Under root of tau naught by rho. This is under root of tau naught is how much? 600 divided by rho. Rho is water, so this is 1000. So from here, can you find the value of V star? Yes. If you can find the value of V star, put the value of V star in this, find the value of delta dash. Find the value of delta dash, put this in this, you will get your answer as I think 8.01, which is greater than 6. Which is greater than 6, indicating that a pipe is a rough pipe. Lekin, in this particular question, it is not asked whether it is smooth or rough. He is just asking the value of K by delta. This is just by my experience. Just by our experience, we are telling that it will be a rough pipe. So my dear students, with this I announce turbulent flow is also over. Now the rest of the problems you can solve by yourself. I have given you an unlimited amount of confidence even in this chapter. Tell me in the comment box whether you have understood. Tell me in the comment box whether you have understood. Can you do more number of numericals by yourself? So things are simple. Just use the equations, find the results. Use the equations, find the results. Come on. Tell me in the comment box whether you have understood this or not. I'm waiting for your replies. ससुरों जिंदा भी हो तुम लोग आज? तुम लोग जिंदा भी हो कि कहीं आखिरी क्लास है तो बस? Very good. Yes. If you have understood each and everything in detail, come to page number 200 of your printout. Come to page number 200. Come to page number 200 of your printout. Come to page number 200 of your printout. Come to page number 200 of your printout. Now let me teach you drag and lift. Now let me teach you drag and lift. We are thoroughly going to enjoy this. We are thoroughly going to enjoy this. Let me start drag and lift. Let me start drag and lift. Let me start drag and lift. Very good. Look here everyone. This drag and lift topic, now why don't you listen to me, yaar? This drag and lift topic is actually not mentioned in our syllabus. It is not mentioned in our syllabus. Then some of the students will say, sir, why are you teaching this thing if it is not mentioned in the syllabus? Yes, you are correct. But beta, this drag and lift topic is actually very important from interview point of view. Also very important from some objective point of views. So though it is not mentioned in your syllabus, but still what I am going to do is, I am not going to go into the details of drag and lift. Listen. I am not going to go into the details of drag and lift. But what I am going to do here is, I have made a capsule. I have made a capsule of drag and lift. 45 minutes capsule is there. 45 minutes capsule is there of drag and lift. Now what I am going to do here is, I am going to give that capsule to you in the next 45 minutes. In that capsule, all the objective question that your teacher has seen throughout his teaching career, throughout the country, whichever exam is there, all the objective questions I will tell you. I will tell you in my explanation. All the interview questions I will tell you in my explanation. Okay? So that, see, to be very frank, this is a gift from my side. This is literally a gift, because this is not part of your syllabus. It is not mentioned in your syllabus. So if I want, I couldn't have taught you this. But still, gift from my side. Gift from my side. A capsule I am giving on drag and lift, so that even a question comes from drag and lift, you are able to give the correct answer in PSUs, other examinations, state level examinations and things like that. Chaliye, let us start with drag and lift. But hey, you should be full on concentrated on the board. Abhyuday, generally the pipes are rough. So if someone is asking that in turbulent flow, friction factor is dependent on what? So basically you are, at that moment you are not saying smooth or rough. You will be saying that it is dependent on Reynolds as well as surface roughness. Pritam Jyoti Deka is asking that, sir, if in any question smooth or rough word is written, can we directly say that it is turbulent flow? Pritam Jyoti, if some data is given to you and you can check the Reynolds number, it is always better that you check the Reynolds number. Otherwise, if the data is not sufficient and you cannot check the Reynolds number, but smooth and rough is written in the question, then take it to be turbulent. Chaliye, let us go for drag and lift. Look here. Very interesting, yaar. We will enjoy. Look here. For example, let us say that there is some aerofoilic shape, something like this is there. Gift from my side. Let us say that there is some aerofoilic shape is something like this is there. And this aerofoilic shape is kept in a fluid which is coming in at a speed of u infinity. Then you know, when the fluid is going to strike with this aerofoilic shape, the first thing is that it is going to create two types of force. One force will be created in the direction of the motion of the flow, and that force is known as drag force. And one force will be created perpendicular to the direction of the flow. One force will be created perpendicular to the direction of the flow, and that force is known as lift force. That force will be known as lift force, and everybody knows that the resultant force, we can find out something like this. Wonderful. So what is the first objective question that they ask from here? Let us focus on all the questions that are asked from this topic. What is the first objective question? The first objective question, they are going to ask the definition of drag and lift. So what is going to be the definition of drag? Very simple. It is the force which is acting in the direction of motion of the flow. And the force which is acting perpendicular to the direction of the flow is known as a lift force. Very good. You know, you are going to get drag and lift whenever there is a relative motion between the body and the fluid. This point is very important. Whenever there is a relative motion between the body and the fluid, or you can say when the body and the fluid are moving in opposite direction, then you will experience drag and lift. For example, if the fluid is at rest and the body is also at rest. For example, if there is air in this room and I am standing like this, I will not experience drag. I will experience hydrostatic force. But when I start to move in this room, I will experience drag from air. So there should be relative motion between the body and the fluid, or the body and the fluid should be moving in opposite direction, then you will experience drag and lift. If the body and the fluid, both of them are at rest, there will be hydrostatic force. There will be no drag and lift. Next, very, very important thing. You know, there can be drag without lift, but there can never be a lift without drag. Very important objective question again. Again I am saying there can be drag without lift, but there can never be a lift without drag. How? For example, let us say that you are having a plate which is kept horizontal in the flow. Now, how many students realize that over this plate, you know, when the fluid is going to come in and strike with the plate, there is only going to be drag over this plate, but there will be no lift over this plate. So therefore, in this particular case, there will be only drag will be present, the lift will be zero. So this type of a body, see, actually, we are entering into the world of aerodynamics. And in the world of aerodynamics, the only thing that two things matters: shape of the body, orientation of the body. Listen to your teacher carefully. Two things in aerodynamics matters the most: shape of the body, orientation of the body. How you're orienting the body is going to decide that what kind of force your body is going to experience. Okay, so therefore, if the orientation of your body is coinciding with the direction of the flow, in this case, this plate I have shown, there will be drag, but there will be no lift. For example, if you keep this plate vertical in the flow, then you know, for example, if this is the plate is there, and fluid is coming in from here, then you know, again this plate will only experience drag, but there will be no lift. Clear, guys? So therefore, look here, there will be drag, but there will be no lift in this case. So beautifully on the board, with the help of two examples I have shown you, there can be a case where there is drag but no lift. But there can never be a case where there is a lift without drag. Because, see, one more objective question. You know, to get a lift force, it is a mandatory thing that the orientation of your body should be inclined to the flow. Because if the orientation of your body is coinciding with the direction of the flow, no lift force is there. If the orientation of your body is perpendicular to the flow, again no lift force is there. So it is guaranteed that your body should be inclined to the flow. Then only you are going to experience a lift force. But when you are going to experience a lift force, 101% drag force will be there. 101%, 100. 101%, 101%, you know drag is going to be there. Are you getting? Yes, sir. So 2-3 things you need to keep care. Already 4 to 5 objective questions I have discussed already. What are those objective questions? Number 1, the force when you keep a body in a moving fluid, or fluid is at rest, body is moving. Whenever such kind of a case is there, there is a force which is generated in the direction of the motion of the flow, which is known as drag force. There is a force which is generated perpendicular to the direction of the flow, which is lift force. If the orientation of there can be drag without lift, but there can never be a lift without drag. Next important thing is, for producing the lift, it is necessary that the orientation of your body should be inclined to the flow. The orientation of the body should be inclined to the flow. Now listen carefully, this is a very important discussion. But I am just teaching you in rough. I told you, na, this is not part of your course. This I am giving you just by my own will. So therefore, you should concentrate. I will draw all the things in rough. For example, let us say there is some bodies there and some fluid is coming in from here. Then you know drag and lift can be created by 2 methods. I will tell you what 2 methods. For example, if I take a very small area on this body, that is dA, then you know over this small area 2 types of forces will apply. Those 2 types of forces is pressure force and shear force over the body. Over this body, 2 types of forces are going to apply: pressure force and shear force over the body. Listen carefully, over any body which is kept in a fluid, 2 types of forces are created. One force is created due to head-on collision of the body with the fluid, and that is known as pressure. And after head-on collision, then the fluid is going to slide over the surface of the body, that will create shear. So basically there are 2 forces are there, pressure and shear. But pressure can create drag and lift, shear can create drag and lift. Pressure can create drag and lift, and shear can create drag and lift. Shear can create drag and lift. And lift, and shear can create drag and lift. Pressure can create drag and lift, and shear can create drag and lift. Look here, how pressure can create drag and lift. Bhaiya, whatever the pressure is acting over your body, there can be 2 components. One component can be in the direction of the motion of the flow, and one component will be perpendicular to the direction of the flow. So this component will create drag due to pressure. This will create lift due to pressure. There can be 2 components of shear also. The 2 components of shear, one component will be in the direction of the motion of the flow, that is drag, and one component will be in the perpendicular to the motion of the flow, that is lift. So pressure can create drag and lift, shear can create drag and lift. For example, look here on the board. So for example, let us say in a fluid, this body is kept in a fluid. Over this body, if you take a small area or something like that, then the fluid is coming in from here. So the first thing is, when the fluid comes in from here and strikes with the body, it is going to create pressure over the body. It is going to create pressure over the body. So that is one of the force. And after creating pressure, then the fluid is going to move something like this over the body, which will create shear over the body. Shear over the body. Now listen carefully. Depending on the orientation of the body, it will be decided that due to pressure, drag will be there, lift will be there or not, or due to shear, drag will be there or lift will be not there. So in totality, total 4 types of forces can get generated over the body. Drag, look here. If you talk about drag force, the drag force can be created by 2 methods. What are those 2 methods through which the drag force can be created? Drag force can be created due to pressure, and drag force can be created due to shear. Same manner, lift force can be created by 2 methods. It can be created due to pressure. It can be created due to shear. I am not saying that in all the bodies all 4 will exist. No. It purely depends on the orientation of the body, that out of all these 4, which one will exist and which one will not exist. So it purely depends on the orientation of the body, that out of all the 4 can also exist. Or it can also happen some of them exist, some of them doesn't exist, depending on the orientation of the body. So, my dear students, there can be a drag which is created due to pressure. The name of the drag which is created due to pressure is known as pressure drag. Or in other language it is also known as form drag. And the drag which is created due to shear is known as skin friction drag. Or simply it is written as friction drag. Now some students will ask, sir, what are the names of these lift forces? There are no names of lift forces. Lift forces is lift only. Acha, listen. See, drag on any body is actually resistance. And resistance will always be there. Because without the resistance, you cannot get the lift. That is the principle now. Because you can never get a lift without drag. Drag will always be there. Some kind of a drag will be there. Either pressure drag or either friction drag. Achha, see, what is pressure drag? See, whenever a body is there, the drag which is created due to head-on collision with the fluid, because the fluid, when it is going to head-on collide with the body, it will create a drag over the body, that is pressure drag. And after colliding, it might move over the body, something like that, that is friction drag. For example, flow over flat plate. In boundary layer theory, I taught you flow over flat plate, So flow over flat plate is friction drag. Very less pressure drag is there. But the most important thing is, drag is not a good thing. An aerodynamic engineer always try to reduce the drag as less as possible. Drag is not a good thing. But wait, what is actually happening is, drag is not a good thing, but drag will always come. Then what should an aerodynamic engineer do? Aerodynamic engineer is saying that out of these two drag, he is trying to figure out which one is more dangerous. See, दोनों के दोनों कड़वी गोली हैं. हिंदी में बोल रहा हूँ जरा 2 मिनट के लिए. दोनों के दोनों कड़वी गोली हैं. सबको पता है कड़वी गोली है और खानी भी है. लेकिन हम फिर ये देख रहे हैं कि इनमें से ज्यादा कड़वी कौन है. So both of them are bitter medicines, but we have to take those bitter medicines. Then we are trying to find out as an engineer that which one is the more bitter. Pressure drag is more bitter. Why? Arey beta, anyone can tell this. Whenever there is a head-on collision with the fluid, the drag which is created is going to be very, very high, and it is very, very dangerous also. So therefore, out of these two drag, which one is more dangerous? Pressure drag is more dangerous. Pressure drag is more dangerous. So it is said in aerodynamics कि friction drag से डर नहीं लगता साहब, pressure drag से लगता है. So what engineers, an aerodynamic engineer, his night, day, complete day, he keeps on thinking that how he should design his body so that the pressure drag is minimized. ऐसा भी हो सकता है कि प्रेशर ड्रैग को कम करने के चक्कर में भले ही थोड़ा फ्रिक्शन ड्रैग बढ़ जाए, हम चला लेंगे. भले ही प्रेशर ड्रैग को कम करने के चक्कर में फ्रिक्शन ड्रैग थोड़ा बढ़ जाए, हम लोग चला लेंगे, लेकिन प्रेशर ड्रैग को नहीं झेल पाएंगे. प्रेशर ड्रैग वी कैनॉट टॉलरेट, दो फॉर रिड्यूसिंग द प्रेशर ड्रैग वी कैन इंक्रीज द फ्रिक्शन ड्रैग. But an aerodynamic engineer, his main aim is to reduce the pressure drag as much as possible. To reduce the pressure drag as much as possible. Now listen carefully. In this case, there are two types of bodies are there. Streamlined body and bluff body. Streamlined body and bluff body. Now what is a streamlined body? A streamlined body is the one, listen carefully. A streamlined body is the one whose orientation coincides with the direction of the flow. For example, अभी बनाया था, ये अपना plate है और यहाँ से the fluid is coming in, so the orientation of the plate is coinciding with the direction of the flow. When the orientation of the plate, when the orientation of the body coincides with the direction of the flow, then pressure drag is less. Pressure drag is approximately 0. It cannot be 0 yaar. It cannot be 0 because some part is perpendicular to the flow so always some pressure drag will be there. But the value of that pressure drag will be minimized. Though the friction drag will be large. But whenever the orientation of your body or the shape of your body is in such a manner that it coincides with the direction of the flow, the pressure drag is minimized. Though we are going to experience friction drag, but our main aim is that we should reduce pressure drag. Hence, streamlined bodies are preferred in the design. Whereas, what is a bluff body? A bluff body is the one in which the body is kept perpendicular to the direction of the flow. This is a complete mayhem. मौत है इधर सीधा. भैया बॉडी को सीधा हेड ऑन कोलाइड करा रहे हो, भयानक प्रेशर ड्रैग क्रिएट होगा. Huge amount of pressure drag will be created. Friction drag will be very, very less. So a bluff body is the one in which the shape of the body or the orientation of the body is in such a manner that the maximum part of the body is perpendicular to the flow, such that the pressure drag is maximized. So out of that, for example, Iron Man or aeroplanes. Why are aeroplanes in air not moving like this? Or why the Iron Man not moving in air like this? Because they know there will be huge pressure drag will be there which they cannot tolerate. So better not move like this, just make your body like this and move like this. Better, streamlined, so that the pressure drag is reduced. For example, let us say, in old days, the cars used to be like this. And the modern day automobiles are something like this. The modern day automobiles are something like this. Now, this is a blunder. Why this is a blunder? Because, fluid is coming in from here. There is a huge order pressure drag is there over this body. And also friction drag is also not less, huge order friction drag is also there. But can you see the shape of this body is much more streamlined in comparison to that body? Yes, sir. So when the fluid is going to come in from here, the fluid streamlines are going to move something like this. There will be less trouble for the streamlines. There will be less trouble for the streamlines is going to be there. So let me teach you a few things. Why design 2 is better. Why design 2 is better. So this is design 1 and this is design 2. See, the first and foremost reason why design 2 is better is design 2 is more streamlined. Design 2 is more streamlined. Now what is the meaning of streamlined? The meaning of streamlined, I have already told you, that the orientation and the shape of the body is coinciding with the direction of the flow. So maximum part of the body and the shape of the body is coinciding with the flow. Such a thing will be called as streamlined. So design 2 is much more streamlined in comparison to design 1. The second good reason will be that pressure drag, which is the main culprit, सबसे बड़ा गुनहगारी यही है और एरोडायनेमिक इंजीनियर के लिए खौफनाक ये सपना है ये. प्रेशर ड्रैग इज मिनिमम इन डिजाइन 2. जीरो तो नहीं हो सकता, जीरो तो कभी हो ही नहीं सकता, लेकिन मिनिमम है, मिनिमाइज्ड है. सो प्रेशर ड्रैग इज मिनिमाइज्ड इन डिजाइन 2. Pressure drag is minimized in design 2. What else? Look here. Why body 2 is better? You know, the point of separation of the fluid, from the body is far apart. The point of separation of the fluid from the body is far apart. What is the meaning of this? You know, fluid is coming in from here, the fluid will get separated out and then the fluid is going to move like this. But the shape of the, भाई देखो सिंपल सी साधारण सी बात है, वो डिजाइन ज्यादा अच्छा होता है जिसने स्ट्रीमलाइंस को जुदा किया तो बॉडी की शेप ऐसी होनी चाहिए कि अंत में वो स्ट्रीमलाइंस को करीब भी ले आए. बट ऊपर वाली बॉडी में देखो, इट इज नॉट डूइंग सो. So therefore the main aim of any body, a body who brings difference in the streamline, the shape of the body should be such that it should also make the streamlines come together after the body. But here you see, even after the body, the streamlines are moving like this. Of course, they will meet after a certain distance, but they will meet after a certain distance, not just behind the body. The shape of the body is not supportive enough. But can you see in this body, the point of, so in the body, the point of separation of fluid from the body is here. In the body, the point of separation of fluid from the body is here. And you can see that the point of separation are far apart. This is not a good sign. This is not a good sign in aerodynamic. This is not a good sign in aerodynamics. But here you see the shape of the body is such that the body is supporting the streamlines to come together to each other, so that the point of separation of the fluid from the body is closer to each other. This is a very good sign. So therefore, why this design 2 is better than design 1? Very simple. Design 2 is better because point of separation of fluid from the body is closer to each other in body 2 or design 2. Now, why this is preferable? See, what is actually happening in if the point of separation are very far apart, then just behind the body very less number of molecules of fluid are there. Just behind the body, very less number of molecules of fluid are there, because the main flow is taking place like this, main flow is taking place like this. So just behind the body, less number of molecules are there, only vortices, edices and things like that, eddies are going to be there. So this is due to this, if less number of molecules are there just behind the body, this will create a low pressure zone behind the body. Molecules are pressure so this will create a low pressure zone just behind the body. And if there is a low pressure zone behind the body, there is going to be a sucking effect. There is going to be a sucking effect. There is going to be a sucking effect. Look here, look here, look here. But you see the point of separation when it is closer to low pressure zone will be created here also. But that low pressure zone will be lesser. So the body is trying to move forward. Behind the body there is a sucking effect. Due to that, additional force is going to get applied. Additional force is going to get applied. So number 4, low pressure zone behind the body is less. Behind the body is less. So if low pressure zone behind the body is less, body 2 is much better than body 1. Now listen carefully. From today onwards, this is a very important interview question. From today onwards, if anyone in the interview, from today onwards, if anyone in the interview asks you what is streamline, what is streamlined body, what is a streamlined body, if anyone in the interview asks you what is a streamlined body, all these are your answers. So if anybody asks you what is a streamlined body, then your answers should be, a body is said to be a streamlined body if the orientation of the body is coinciding with the flow, such that the pressure drag on the body is minimized and the point of separation of fluid from the body is closer to each other, so that the low pressure zone created behind the body is less. Such a body will be called as a more streamlined body. Such a body have streamlined body. Wonderful, wonderful. Look here, please kindly look here. Kindly look here, beta ji. Please, it's my humble request. Look here. Let me discuss one more very important interview question and a very important phenomena, Magnus effect. Magnus effect. Now, what is Magnus effect? Whenever a sphere or cylinder. So Magnus effect you are going to find over rotating sphere or cylinder. Magnus effect you are going to find over rotating sphere or cylinder. Whenever a sphere is rotating in a fluid or a cylinder is moving and rotating in a fluid, they are going to experience an additional lift force, and such a thing is known as Magnus effect. Due to this rotation, they will experience an additional lift force, and that is known as the Magnus effects. That is known as the Magnus effects. That is known as the Magnus effect. Look here on the board. For example, Yajuvendra Chahal, India ka spinner. For example, Yajuvendra Chahal is throwing the ball like this. For example, if Yajuvendra Chahal is throwing the ball like this, and the commentator is saying, what a flighted delivery, what a beautiful flighted delivery by Yajuvendra Chahal, then my dear students, Yajuvendra Chahal is not doing anything. Everything has been taken care by fluid mechanics. So this is a sphere is there, the cricket ball is a sphere, and when Yajuvendra Chahal is throwing that cricket ball something like this, so when that spherical cricket ball is rotating in the air like this, somewhere in the flow, in the motion of the ball is going to experience a bit of lift force. And due to that lift force, what is going to happen is the batsman will get disguised. Why the batsman will get? Because the batsman is looking at the hands of Yajvendra Chahal. Na? So according to the hands of Yajvendra Chahal, the batsman will try to gauge the trajectory of the ball. And by the trajectory of the ball, he will say, okay, the ball is going to land here. But as it is a rotating sphere, it will experience a bit of lift force somewhere in the middle of the movement. So due to that, wherever the ball was to land, the ball will land a bit closer to the batsman. LBW decision is going to be there. LBW decision is going to be there. Cristiano Ronaldo, CR7. Cristiano Ronaldo, most of his kicks, when you are going to see, you are going to apply the kick like this, you will think like at the first moment the ball is not entering the goal post. But what will happen in the middle is the ball will turn, so, and it is going to enter into the goal post like this. In volleyball, what you do is, overhead service, when you hit the service like this, then it is okay. But what you do is, you take your palm like this and you hit the ball like this. So the volleyball is going to, in service itself, the ball is going to move something like this. It is going to swirl. Table tennis is completely a game of Magnus effect. In table tennis, the shot itself is known as top spin. So when you are going to play it, top spin like this. So you spin the racket ball like this, spin the ball like this. Everything is Magnus effect, my dear students. Look here on the board. Now how this effect is created. For example, if there is this spherical ball or cylinder is there, but remember, these are not on stationary cylinders or spherical balls. These are on rotating spheres or cylinder. These are on rotating spheres or cylinder. Let me divide this ball into two parts, and let us say that the ball is rotating like this in the flow. So ball is rotating like this and it is moving in the flow like this. So the flow is 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 like this. Now listen carefully. If your flow is like this, just look at the upper part of the ball. Just look at the upper part of the ball. In the upper part of the ball is rotating like this. The fluid is also moving like this. So the motion of the flow is coinciding with the direction of the motion of the ball. Due to this, the velocity of the molecule which are above the ball will increase. Because the ball is also moving in the same direction, fluid is also moving in the same direction, velocity will increase, pressure will decrease above the ball, hence above the ball low pressure zone will be created. Whereas below the ball, if you will see, the ball is rotating like this, so the direction of the motion of the ball is like this, the direction of the fluid flow is like this, so that is in opposite direction. Due to this opposite direction, there will be resistance to the motion of air, and due to this resistance, the velocity is going to be lesser, pressure is going to be higher, and hence high pressure zone is there below the ball. And due to this small pressure difference, the ball is going to experience a lift force over it. And this is known as the Magnus effect. This is known as the Magnus effect. This is known as the Magnus effect. Today you will realize how Pathak sir has dealt with the subject in in-depth analysis. Today you will realize this. How much practically your teacher has literally struggled in this classroom for hours for teaching you the practicality, the best possible fluid mechanics in a stipulated amount of time. All this stuff you are able to visualize and enhance because already your teacher has told you all this stuff. Look here. There is another very important case. Sphere moving in a fluid. Please look at the heading. Please look at the heading. This is not a sphere which is rotating in a fluid. This is just simply a sphere which is moving in a fluid without rotation. Without rotation. So for example, if this is a sphere is there, and let us say this sphere is just moving in a fluid without rotation. Okay, then you know the drag force over this sphere, very important formula, drag force over this sphere is given by 3 pi mu u infinity into diameter of the sphere. 3 pi mu u infinity into diameter of the sphere. 3 pi mu u infinity into diameter of the sphere. 3 pi mu u infinity into diameter of the sphere. Now some students will say, sir, how this term is coming? See, listen. Drag and lift. What is the formula for drag and lift? You have been studying this from your college life, yaar. Because I know in most of the universities this question is asked in the college itself. So what is drag force? Drag force is coefficient of drag multiplied by half rho a u infinity square. What is lift force? Lift force will be CL over the body into half rho a u infinity square. Now I see your teacher has beautifully explained in boundary layer. Beautifully I have explained in the boundary layer this CD, the utilization of this CD. So this is from experiments. Scientists, they find out the value of CD for a particular case and that is given to you in the question paper. Just you need to multiply by half rho a u infinity square to get the total drag over the body. To get the total drag. Achha, one more thing. Let me, when I'm talking about this, beta, there is a problem in this A. I hope you guys know. This A is very critical in this formula. This A is not the total surface area. This A is actually maximum projected area in the flow. In this particular formula, A is not the surface area, it is the maximum projected area in the flow. For example, spherical ball is there, and if this spherical ball is moving in air, so you need not take 4 pi r square. You have to take, for that sphere, the projection will be a circle. You have to take the area of that circle. Arey, do you remember hydrostatic force curved surface? Do you know how to take projection of anything? Yes. For example, if this is your mobile is there, and if this mobile is kept like this in the flow, don't take the total surface area. Blow a torch over this torch, there will be a projected rectangle will be there. Take the area of that rectangle. Take the area of that rectangle. So this is, let me see whether this is written in your printout or not. Otherwise, yes, it is written. On page number 201, it is written. On page number 201, it is written already. So some students will say, sir, how does this formula come? Look here. You have to find out drag force. Drag force will be CD over the sphere half rho a u infinity square. है ना? U infinity is the velocity of motion of the sphere. Area will be the maximum projected area in the flow. Then what is the maximum projected area in the flow? It's a sphere moving in a flow. It will be a circle. So circle is going to be pi by 4 into d square. So okay. So to find the drag force, half is known. Rho को rho ही रहने देने का. Area is pi by 4 d square. U infinity square. CD. My dear students, the CD for a sphere moving in a fluid was given by a very famous scientist with the name Stokes, and from his experiments he gave the value of CD of a sphere moving in a fluid is 24 by Reynolds number. Very famous formula. Very famous formula. 24 by Reynolds number. 24 by Reynolds number. But this is only applicable when Reynolds number is less than 0.2 or 0. Some books write 0.2, some books write 0.1. So I am writing 0.2. But you know, in most of the cases, Stokes' law is applicable. So this is 24 by. So what you do is, in this place of CD, you write 24 by Reynolds number you write rho u infinity d by mu, area you put this, cancel out all the stuff, you will get this answer. So what is the formula for drag acting over a sphere? Come on guys. What is the formula for the drag acting over the sphere? The drag acting over the sphere is 3 pi mu u infinity into diameter. Let me teach you one last thing also. There is a very famous question, sphere settling in a tank. Sphere settling in a viscous medium, sphere settling in a tank, sphere settling in a viscous medium, sphere settling in a tank, sphere settling in a viscous medium. Now what will be asked? And then they are going to ask you, find the terminal velocity of sphere. Find the terminal velocity of sphere. This is a very famous question that they ask. Some students in the comment box, they are asking for aeroplanes. I really don't know whether you people are studying or not, but that video playlist that I have given you now, in that video playlist, aeroplane is already there. Terminal velocity is already there. So after attending today's lecture, your first and topmost priority is go to the playlist. In the playlist, there are videos of aeroplane. There is one very important video, why golf ball has dimples. You see, have you ever seen a golf ball? That golf ball is having dimples over it. 300 to 400 dimples are there over the golf ball. Then the question that they ask in interview is, why can't we use a normal spherical ball for playing golf? Why are we using dimpled ball for playing golf? That is a very, very important interview question. So I have already shared the videos of few Magnus effect video I have shared. I have shared the videos of terminal velocity. I have shared the videos of aeroplane. I have shared the videos of your golf ball. Because when you see all this stuff in the videos, then your brain automatically gets enlightened. Now what is this question? See. For example, let us say this tank is filled with a viscous medium having a viscosity mu. Now what is going to happen is, you are going to put a steel ball or iron spherical ball into this viscous tank. So when you just drop an iron or steel ball into this viscous medium. So what will happen? At the starting, as soon as you drop this ball, the ball will accelerate at the starting. Because the forces are unbalanced over the ball. Why the forces are unbalanced over the ball? Because the weight of the ball is larger than the drag which is acting initially over the ball. So what weight is acting in downward? Arey Baba, for example, if this is a sphere is there. If the sphere is moving downward, then the drag is a force which is opposite to the motion. Drag over the ball, spherical ball will act in opposite direction. The drag on the ball will act in opposite direction. Getting my point? So when you drop the ball initially, the weight of the ball is larger than the drag acting over the ball. Because the drag acting over the ball will depend on the velocity of the ball. But at the starting, the velocity is less. Weight is large. So this is the reason why downward force is more in comparison to upward force. So the ball starts to accelerate in the downward direction. But when the ball starts to accelerate in the downward direction, after achieving a certain velocity, the drag force, because as the ball's velocity keeps on increasing, the drag force over the ball also keeps on increasing, and weight is fixed. So earlier weight was higher, drag force was less. But as the ball started to accelerate in the fluid, the drag force also kept on increasing, and there will be a certain velocity where the total downward force over the ball and upward force over the ball will get balanced out each other, and that velocity is known as terminal velocity. So whenever anything is dropped into the fluid, have you seen parachuter from people skydiving? So in skydiving, initially the body accelerates, but after some time when you are like this, your forces over your body becomes balanced and you start to come down with a constant speed. When you achieve that constant speed, that is known as terminal velocity. That is known as terminal. So when will you achieve terminal velocity? When the forces are balanced over anything. So for example, here the sphere is moving. So sphere is moving downward. Sphere is a completely submerged body in this fluid. So the first force which will act in upward direction is the buoyancy force. Second force which will act in upward direction is the drag force over the sphere. Third force will be the weight of the sphere, which will act in downward direction. Third force will be the weight of the sphere, which will act in downward direction. When all of them will get balanced, then it will start to come down at a constant speed. So therefore, how to balance? Drag plus buoyancy is equal to the weight. Drag plus the buoyancy is equal to the weight. Drag plus buoyancy is equal to the weight. Beta, what is the drag over the sphere? 3 pi mu u infinity into diameter. Just previously I have taught you. Buoyancy everybody knows, rho of the fluid into g into volume of the fluid displaced. Into volume of the fluid displaced. Very good. And what is the weight? What is the weight? Weight is nothing. Weight is again rho of the body into g into volume of the body submerged, which is again volume of the body. So equate all of them. When you equate all of them, find the value of u infinity, and that is terminal velocity. Already in your printout it has been found. Complete batch. But after listening to this lecture, after the class, you have to look at the videos which I have sent you in the playlist. You have to look at those videos. Complete batch, complete batch. Tell me in the comment box whether you have understood each and everything beautifully or not. Very good. So all the things which I have taught to you are already there in your printout, except this. Except this. So come to page number 203 of your printout. Come to page number 203 of your printout. On page number 203, please take this complete board. Come on, come on. Please take this on page number 203 of your printout. Done, completed this. Can I change the slide? अगर ये कंप्लीट कर लो तो डन लिख देना एक बारी कमेंट बॉक्स में. प्लीज राइट डन इन द कमेंट बॉक्स इफ यू हैव कंप्लीटेड दिस. Yes, done. One more thing is missing in your printout. Magnus effect. Magnus effect. Page number 202. Page number 202. Diagram is made, but that diagram is incomplete. So you please complete the diagram and also write this rotating sphere or cylinder. Wonderful. Yes. Beautiful day today. Beautiful day today. Early morning classes are always wonderful because we are ahead of the world already. We are ahead of the world already in terms of knowledge, in terms of everything. Very good. Done, beta. I hope this is completed. Chalo, now we will stop for a break. Now we will stop for a break. When we meet after the break, then we will continue with the other remaining topics. Okay? So we will be stopping for a break, and when we meet after the break, we will be continuing with the other topics which are left in our course. So we are meeting at 10:30. So a bit longer break I am giving you today. A longer break I am giving you today. Okay, so we are meeting at 10:30. We are meeting at 10:30 a.m. So let us stop for a break. Let us stop for a break. We are meeting at 10:30. We are meeting at 10:30. Okay? Chalo, it's a break. It's a break. 10:30.